Hello everybody, welcome to today's lecture. So today we're going to talk about the rest of 2.3 and then we're going to talk about 2.4 and 2.5 because they're both very short. So after today we'll actually be done with chapter 2. So make sure to look at your announcements for information about the chapter 2 exam. Okay. So let's go ahead and jump right into the next part of 2.3. Remember last time we talked about standard deviation and variance. So remember the difference between the population standard deviation and the sample standard deviation. And make sure you know how to calculate this somewhere, whether it be by hand, in a calculator, on Excel, on Google Sheets, something like that, okay? I showed how to do it in Excel. If you need to know how to do it in Google Sheets, let me know. It's pretty much the exact same thing. You just where you find the formulas are different. And if you don't like either of those options, just go ahead and type into Google standard deviation calculator. And the first few results I checked out yesterday, and they were all pretty straightforward. You just type in your data, select whether it's a population or a sample, and it just calculates it for you. Okay. I'm not going to ask you to calculate standard deviation by hand, especially with this online format, okay? Because it would be hard for me to even have you submit that anyway, okay? And also, in practice, this is hardly ever done by hand. I calculate standard deviation quite often, but I don't really ever calculate it by hand. I use some sort of computer program to do it. But it's important to know how to do it by hand still so that you know what's going on. And so we know what the standard deviation is, which is the average distance our data is from the mean. Okay, that's what the formula is telling us. So there's only a little bit more to talk about in 2.3. We're not going to go into too much detail with the rest of it. We're not even going to look at really any more formulas. We're just going to kind of talk about the concepts. Okay, so this section is called percentiles. So what's a percentile? You've probably encountered these in some way before. If you've ever taken a standardized test and you've looked at your score, you probably got back a percentile. Or, if you've ever taken like a kid to the doctors or something when they're really young, oftentimes they'll tell you their percentile for height or weight. What does that mean? What does the percentile mean? Well, a percentile gives you a number that tells you that all of the data, that whatever percent of the data is at or below this number. So, for example, if we score in the, let's say 60th percentile on an exam, or rather like on a standardized test, you score in the 60th percentile on a standardized test, that means we scored at the same level or better than 60% of everyone who took the exam or the test. Okay. So if you get like, your ACT score or your SAT score or whatever, and it tells you got in the 60th percentile that means that you scored better or the same than 60% of people. In other words, 60% of people scored the same or worse than you. Okay. So if you mapped out everybody who took the exam, this is the 60% mark, then there's 60, this is the 60th percentile, then 60% of people are in this section, meaning they did worse than you. And around 40% of people are in this section, right? Meaning they did better than you. Okay. So you can, there's a chart online where you can check, the ACT scores. Like, for example, if you get like a 30, it's like the 95th percentile. If you get like an 18, it's like the 36th percentile, etc. And you can convert your scores into percentiles. And it's actually different for every subject too. Like an 18 in English and an 18 in math don't put you into the same percentile necessarily. They map them in the different percentiles. So there's a whole chart online if you Google ACT percentiles that will give you a better understanding of it. The other example I talked about was, often when you take a kid to the doctors, when they're really young, as they're growing up, they'll often tell you like they're in the 90th percentile for height or the 5th percentile for weight or something like that, right? If they were in the 90th percentile for height, that would mean that they're taller or the same height as 90% of kids their age, right? If they were in the 5th percentile for weight, that would mean that they weigh the same or more than only 5% of kids their age, right? So it's basically telling you how much of the data is below this point. Okay. There are some special percentiles that we often talk about called quartiles. Okay. So let me write out the definition for percentile first, though, because I just used an example there, but I didn't actually write out the definition. So a percentile is a value with k percent, where k could be any number, of the data at or below this point. Okay. So you could have the 50th percentile, you could have the 100th percentile. That would be the very top of the data, right? You could have the 7th percentile, etc. All right. So quartiles are just special percentiles. Okay. So we call the 25th percentile the first quartile. Okay. Which we abbreviate as Q1. So it's like we're dividing it into quarters, right? So we have the first one happens at the 25th percentile, the first quarter. So the first quartile tells you, okay, 25% of the data is at or below this point. The 50th percentile is called Q2, or the second quartile. Okay. Note that this is also the median. because this is where 50%, this is the exact halfway point of our data, right? Which is the same definition we had for the median. So Q2 and the median are the same thing. The 75th percentile is called Q3. Okay, your third quartile. So 75% of the data is at or below that point. And finally, the 100th percentile is called Q4. Now, we don't really talk about this one too much. Oftentimes, it's not even listed. Like in the book, it doesn't even list Q4 because this is just your maximum data point. This means that 100% of the data is at or below this point. So it's just the biggest point. So you could just think of this as the maximum. So we won't usually worry about this one too much. And so Q4, we don't really worry about. Q2, we just often call the median. We don't usually call it Q2. So Q1 and Q3 are really the special ones here. In fact, we use Q1 and Q3 to come up with a special thing called the interquartile score. Okay. Or interquartile range, sorry. Or we abbreviate that IQR. Okay. So the IQR tells us how much of the data lies between the 25th percentile and the 75th percentile. Okay. So the way we would calculate that is by taking the 75th percentile Q3 and subtracting off Q1. Okay. So if we have our data, right, here's where we start. Here's Q1, the 25th percentile. Here's Q2, the 50th percentile. Here's Q3, the 75th percentile. And here's Q4, the 100th percentile. Then the IQR is this part. Okay. So right in the middle here, because this is usually the data we're most interested in, is the data that's closest to the center, right? Closest to the median. The ones on the either extreme are usually the outliers, right? They're either the ones scoring super well or super bad. So if we want to know what's like more common, what the average, what kind of data is close to the average, we usually look at the IQR, that part right in the middle. And we would make decisions based on the IQR usually, right? So to calculate it, like I said, you do Q3 minus Q1. Let's talk about how we would find these numbers, because we didn't talk about how to find the quartiles. So let's look at an example here. Let's look at our trusty test score example. I won't use the exact same numbers, but okay, so let's say that these are our test scores. Okay. And let's try to find Q1, Q2, Q3. Okay, we don't need to find Q4 because Q4 is going to be the biggest one, 91. I guess I can go ahead and write it down though. Right. So the easiest one to start with is usually Q2 because that's the median. Okay. And we know how to find the median from the earlier section. We just find the exact middle number. So we start at the ends at 0 and 91, and then we count inwards. It's usually easier to use like your fingers, which I can't really show you here. But so we'll start at the ends, and we'll count in, and then in again, in again, in again, and then we're going to meet at 68. Okay. So Q2 is equal to 68, which is the median. So that's the 50th percent mark, right? And let me like highlight that, circle that in red. Okay. So how would we find Q1? Well, let's think about what Q1 is. It's the 25th percentile, right? Q2 is the 50th percentile. So Q1 should be exactly halfway between the first data point and the 50th percentile, right? AKA like the 0th percentile and the 50th percentile. So it's like the median of the first half of our data. Okay. So let's think about how we would find that. Okay. So we're looking at this part right here. Hang on, let me check something real quick. Okay. So we're looking at these numbers right here. Okay. We already found Q2, so we're not going to include that one. We're just going to look at these 5. Okay. So what's the median of these numbers? Well, there's 5 of them. So if we start at the ends and count in, we meet at 55. So Q1 is 55. Q3, similarly, it's the 75th percentile. So it's exactly, it's like the median of the second half of the data. Okay. So these numbers. So what's the median of these numbers? Well, exactly in the middle is 81. Okay. So it's going to be 81. So here's our first quartile, our second, and our third. And we don't really need to worry about Q4. So now let's calculate the IQR. Okay. This is equal to Q3 minus Q1. So that's going to be 81 minus 55. Okay. Just 26. Is that right? Yeah. So this tells us that the middle part of the data is 26 points. There's a spread of 26 points. Okay. Okay. So let me show you how to do this in Excel also. So we'll type in our data 0, 40, 55, 56, 62, 68, 75, 78, 81, 90, 91. I'll show you how to do it in Google Sheets also. So we're going to use let me make some labels here. So Q1, Q2, Q3. Okay. So we're gonna do the same thing. Start the same way as last time. We're gonna go to formulas, more functions, statistics, and then if you go down, you should find some quartiles. Okay, so there's quartiles included or quartiles excluded. Um, so the difference is whether or not you're including the extremes of the percentiles, like whether or not you're including the 0th and the 100th. So typically we are going to use the included one. So we'll do quartile included. On Google Sheets, there's one that just says quartile. So for the array part, that's asking you what your data is. So you don't have to type anything there. You can just go to your data and highlight all of it. Okay, so you click the first one, keep holding it, and then drag it down. And then it'll automatically fill it. For the second one, this is asking you which quartile you want. Okay, so you can just press 1, and it's actually giving us 55.5. Interesting. I think that's because the way we did it the first time is because we did the excluded version. Let's test it out. Yeah. So it doesn't really matter which one you do. So the reason, so we got 55 basically because we didn't include 68, so we were excluding it. And that's the way the book did it. Sometimes, that's what I was pausing and checking actually, is sometimes you do include the 68. If we did include the 68, and when we went to find the median, we would have got a tie between 55 and 56. And then we would have got the 55.5. Okay. So it's really not a big deal which one of these you choose. Okay. If you'd report either of these answers, I would accept it. Okay. Now Q2, it should be the same either way. Because it's the median. Let's check though. So I'll do the included one first for all of these and then the excluded one second. So that's the included one, 68, which is what we got. And 68. So it ends up being the same thing. And then we'll go to Q3. Notice you can also do percentiles. So quartiles are special percentiles, but if you wanted to do actual percentiles, like if you wanted to do on the 90th percentile or the 52nd 0.5th, you could do that. So let's go ahead and do this one. So we want the third quartile now. So it's 79.5. Again, they're getting a tie between 78 and 81. If we do the excluded version, or we don't include the 68, then we'll get our answer, which is the 81. Okay. So there you go. So this first column is the included one, where we're including the 68 on both sides. And the second column is the excluded one where we're not including the 68. So this one is how the book is presenting it. I was teaching this to another class with another book, and it was presenting it with this one. So it really just depends on the context. Okay, so you can do either one of these. I won't mark you wrong either way. Let me get Google Sheets pulled up for you guys. All right, I got Google Sheets pulled up. This is that I was using yesterday, so let me clear it out. And let's go ahead and get our data in there. 0, 40, 55, 56, 62, 68, 75, 78, 81, 90, 91. Okay, so the reason I'm showing Google Sheets, if you don't know, Google Sheets is free, just with any Gmail account. Okay, so anybody can make this and it's free, unlike Excel, which isn't really free. A lot of computers come with Excel, but it's not actually technically free. You might be able to get it like through the school or something, I'm not sure. But nonetheless, Google Sheets is free for everybody, and it can do most things Excel can do. I don't really know the nitty-gritty differences between them, but I do know that, all like the surface level stuff that we're going to be interested in, they can definitely handle that. Maybe I'm sure there's more technical differences if you really got deep into both of them, but we won't worry about that. So let's look for Q1, Q2, Q3. Let me also show you the standard deviation for Google Sheets, because like I said, I would recommend calculating standard deviation either in this or in an online calculator. So let me show you how to do it. I showed you how to do it in Excel last time, but not in Google Sheets. Okay. So everything's almost exactly the same. The difference is where you find the formulas, and that's going to be right here. They call them functions instead of formulas, but they're the exact same thing. So this button, which is a capital sigma, that's like the notation we were using for averages. Whoops. We just go ahead and click that, and then here's your functions. And they're divided under different headings, but they still have a statistical one. Average, that would be what you'd use for like the mean, right? So we'll go to statistical, and we'll go down to quartile. So notice they have quartile, quartile excluded, quartile included. So let's see which one quartile gives us, because I'm not sure. So the only difference is it doesn't have like that box that Excel pulls up, so you have to do it a little more manually. So we'll still highlight the data. The only difference is now you have to press comma and then press what your quartile number is. You can see in the box that pops up right here, it's telling you the syntax, meaning like what to type in. So it says first put your data, which we did, then comma, then the quartile number. Okay. And then it gives you an example. So we'll just do 1, and it'll return 55.5. So by default, if you just press quartile, it gives you the included version. So if you want the excluded one, which is what our book is doing, you just do quartile excluded, comma, 1. Okay. Q2, you could do second quartile. You can also just do the median. Let me do it that way just to show you. And then you don't have to type anything else in. You just get 68. You don't have to do the comma or anything, because you don't have to specify the quartile. And then Q3, we'll do, let me just show you, like with percentile, you can do this in Excel too. You can do it this way. You can highlight the data, and then you have to type in which percentile you want as a decimal. You can see in the example here, they do it as a decimal. So Q3 is the 75th percentile, so we'll type in 0.75. Okay, and there we go. So then if we want the quartile excluded, like the book, highlight the data, comma 3. Okay. Let me move this over. So now just to show you how you do it in how you do the standard deviation in Google Sheets, we go down to statistical. We want to find the standard deviation. Remember, there's standard deviation for population and sample. Okay, so you have to really make sure you're clicking the right one, because they're calculated differently. So they're going to give you a different number. Let's say this was a sample. Okay. We would just click that, and then all you have to do is highlight your data. Okay, you don't have to do anything more, and press enter. Okay. If it was a population, you would do the standard dev.p, highlight the data, press enter. Notice these numbers are very different, so make sure you're using the right one. The problem should tell you if it's a population or a sample. You just got to look for that word somewhere in there. Okay, so let's get back to this stuff now. So we're done with 2.3 now. So like I said, and also just so you know, the book shows you, it takes you through how to do this in a TI-83 calculator or a TI-84 calculator. It's the same way, which is like the standard graphing calculator that most people use. If you happen to have that, that's great, and you can use that. But I'm not requiring anybody to use it, which is why I haven't gone through it. If you want it, if you have one and you want to know how to do that, I could probably help you with it. I haven't used one of those calculators in a long time, so I would just need to refresh my memory on it. But let me know if you want me to show you, to walk you through how to do it on there. So let's go down to 2.4 now. 2.4 is short, but it goes through something that is very important. And that's what's called the normal distribution. All right, so the normal distribution is what we sometimes refer to as like the bell curve. Okay, like falling. You might like hear some expressions of like falling within the bell curve or something like that. It's referring, or it should be referring, to the normal distribution. Okay, there's a lot of different types of distributions. What a distribution is in general is it kind of tells you how your data is distributed. So like you take a bunch of data, you plot it on a graph, and it is usually in the shape of some kind of distribution. Okay. The normal distribution is called, it's referred to as the normal distribution because it's like the most common one. Okay. There's some laws in probability that basically tell us like if you do a lot of stuff enough times, eventually it's going to look like a normal distribution. Okay. So it's the most commonly used distribution in statistics. So it's the only one that we're going to go through. If you took like a full-fledged statistics class, they would probably take you through a bunch of different distributions. Like if you take the one here at Simmons, we would go through a probably like 7 or 8 of the different distributions. Okay. So let's look at what this looks like first of all. I almost think I would rather actually go ahead and grab the picture, so let me do that. Okay, so I pulled up chapter 2 from the book here. So let me show you guys this picture, and I'll just copy and paste it into the notes, because I think it's important to really see the full picture instead of me trying to just draw it. So this in general is what a normal distribution looks like. Okay. So it's the bell curve. You can ignore for a second like the 68%, the 95%, all that stuff. The curve itself is what's called the normal distribution. Okay. So this is like if you plotted all of your data, a lot of things end up being normally distributed. For example, like heights in humans, if we looked at the heights of everybody and we plotted all of them, a lot of them would look like this. What's special about the normal distribution is what these arrows are saying right here. This middle part is the mean. Okay, this is the mean. And remember, sigma is the standard deviation. Okay. So this part right here from sigma minus, or the mean minus the standard deviation to the mean plus the standard deviation, this is what we call one standard deviation away. And what we see is that 68% of the data in normally distributed things are within one standard deviation from the mean. That's a lot of the data, right? That means most of it is pretty close to the mean. What's even more surprising is once we open it up to 2 standard deviations away, 95% of the data is within that range. So if you just think about like height, if we knew like the average height and what a standard deviation of height is, 95% of people are within 2 standard deviations from the mean, which means that 95% of people are like around the same height, which is very surprising. Like that's not what we would expect. But when we plot out of the data, all of the data, that's what it shows us. And it turns out a lot of things are normally distributed, meaning a lot of things have most of the data within 95% of the mean. And then you keep going within 3 standard deviations, 99.7% of data falls within there. So there's only 0.3% left for what we call the outliers, right? The ones that are really far away. So like people who are really tall, for example, I don't have the exact numbers, so I don't want to like misspeak and say what the actual height would be, but people who are really tall or really short, they're only making up 0.3% of the population. Most people are within that 99.7%. But like I said, it's not just height. There's a lot of things. So this here, let's look at this example that's in the book here and how we would use this, okay? So this is what's called the empirical rule. So we'll go through this example. I don't know if there's a way for me to make this bigger. Let me check. Oh yeah, it looks like I can. There you go. Let's make it even bigger. There we go. First of all, the empirical rule says exactly what's it said in this picture here. Let me move this down so I can write it. The empirical rule says if a data set is approximately normally distributed. Okay, why are we using the word approximately, first of all? Well, oftentimes, if we wanted to know whether something was truly normally distributed, we couldn't really do that by looking at a sample. We would have to look at the entire population. So we're typically just looking about, we're typically just looking at a sample, and we can usually only say whether or not it is approximately normally distributed. Empirical means basically what does it look like? Okay. So if it looks like it's normally distributed based on our sample size, then we can use the empirical rule here. Hang on, I'm having trouble getting my pen to work. Let me fix this real quick. Okay, sorry about that. So I got my pen working. So if a data set is approximately normally distributed, then we can use what's called the empirical rule. Okay. So this says approximately, let me just write APP, 68% of the data is within one standard deviation from the mean. Okay. Approximately 95% is within 2. So I'll just write that. So approximately 95% is within 2 standard deviations from the mean. And approximately 99.7% is within 3. Okay. Just like the picture says right here. Okay. So let's see how this works in practice. So suppose that your class took a test and the mean score was 75%. So our mu, our population mean, because we're talking about the entire class, so it's like a population, our mu is 75%, and the standard deviation is 5%, it says. Okay, so the mean is 75%. The standard deviation is 5%. So remember, we're using the Greek letter mu for 75 for the mean, the Greek letter sigma for the standard deviation. If the test scores follow an approximately normal distribution, meaning we can use the empirical rule, answer the following questions. A, what percentage of people had scores between 65 and 85? Well, let's think about it. Right, if this is 75%, then one standard deviation away, well, 5% away from 75% in this direction is 80%, right? How am I finding that? I'm just doing 75 and adding 5, right? So we're moving 5 in the positive direction. And on the other side, going 5% over from 75 this way gets us to 70%. So one standard deviation away, let's say one standard deviation is between 70 and 80%. Okay. Because we're just moving 5 in both directions. So we're moving 5 spaces. If we wanted to move 2 standard deviations, well, 2 standard deviations would be 10%, right? Because 1 is 5, so 2 is 10. So we're going to move 10 in both directions. So 10 in each direction would be going to 85 this way, because we're doing 75 plus 10. In the other direction, it's 65, because we're doing 75 minus 10. So 2 standard deviations is between 65 and 85. Okay, and that's what this question is asking us. It's asking us what percentage of students had scores within 2 standard deviations from the mean, basically. So if we go up to the empirical rule, that's this part right here. 95% is within 2 standard deviations from the mean. So the answer for 2 is 95%. Okay. All right, what about B? Actually, let's skip ahead to C because we already answered C here. C asks what percentage of the students had scores between 70 and 80. Well, that's within 1 standard deviation, which we already found right here. The empirical rule says that 68% of people will have scores within 1 standard deviation. So the answer for C is 68%. Okay. B is asking about between 65 and 75. Well, let's go back up to our picture here. So for our data, this is 75. This is 80, this is 70, this is 65, this is 85, this is 60, this is 90. Okay, this is like putting our numbers in. Well, so you can see like between 70 and 80 is 68, like we said. Between 65 and 85 is 95, like we said. What about between 65 and 75? Well, between 65 and 85 is 95. And notice that this is symmetric on both sides of the mean. One property of the normal distribution is that exactly half of the data is below the mean and half of the data is above the mean. In other words, the mean and the median are the same thing. So, which we can see from the picture here. But that means that between 65 and 75 is it going to be exactly half of 95. So it would be 95% divided by 2, which would be 47.5%. Yeah, and we can see the answers here. So you can see B, 47.5%. Okay. All right, so it's exactly half here. Half of 95 is 47.5. Okay. All right, so finally, what percentage of students had scores above 85? Well, let's go look at our picture since we already put the data on here. What percentage is in this range? That's a little tricky. We really need to think about this, okay? What percentage of students... Let me see how to best explain this. We want this region. Okay. So what do we know? Well, we know where 95 and 99.7 are, right? This is where 95 of the data is, between these parts. This is where 99.7 of the data is. Okay. We can use that information to find how big this is, this part. Okay. So notice 99.7 minus 95 is 4.7%, which means that this part and this part in total must make up 4.7%, right? Because that's the region between 99.7 and 95. That's the extra part after 95. Now we're only interested in this one in particular, so we divide it by 2. So 4.7 divided by 2 is what we're looking for here, which is going to be 2.35. So this part is 2.35%. Okay, so we're almost there. We found this part. We just need to know about this part. Well, this section and this section is what's left over after 99.7. Okay, so altogether we have to have 100%. 99.7% is already taken up, so that leaves 0.3% for the red region. Again, we're only interested in 1/2 of it, right? We're only interested in this part, so we want to divide that 0.3 by 2. Okay, so we end up with 0.15. So in total, we're looking at 2.35 plus 0.15. Okay. So these regions together will be our answer. So we're going to go ahead and do 2.35% plus 0.15% to give us a total of 2.5%. Okay. And let's check. And this is the answer. And you can see the book actually did it differently. So that's good. So you can look at this one if maybe that explanation didn't make much sense. I know it's a little confusing. So don't expect to get it the first time you hear it. Make sure you go back through that example and understand what was going on here. Maybe try to do it your own way. You really want to look at like how we can manipulate this picture and how we can think about the different regions. Okay. So feel free to pause the video and go back through that part slowly. Okay. And look at what the book did too, if that one didn't make as much sense. So we essentially want to look at, okay, how do we divide these regions? Based on the fact that we know this is 68, this is 95, this is 99.7. It's kind of like more similar to what you would do in a geometry class. So that could be good or bad depending on your preferences. All right, let's go on to the next part. That's actually, oh no, there's one more thing for 2-4 here. So I know we're going a little long. So I'll just go through this quickly. All that's here is called the z-score. Okay. The z-score is kind of a way of standardizing our data to look at one score. The z-score is given by z equals our data minus the population mean divided by the population standard deviation. Okay. So x is the data value. Mu is the population mean. Sigma is the population standard deviation, just as it's always been. And our z is what's called the standardized value. Okay, or the z-score. Okay. So, I mean, there's really not a lot to say about it. I really just want you guys to be aware of this because a lot of times people use z-scores. And the main idea is that a usual value has a z-score between -2 and 2. Okay. i.e., -2 is less than z, which is less than 2. It's between -2 and 2. Okay, that's for a usual value. So an unusual value would be somewhere outside of this range. And as the name implies, the usual values will be more common. The unusual values will not. Okay. But like I said, I don't really want to go too much into it. There's not a lot to talk about with it. Okay. Just be aware that it exists. The z-value is very commonly used in other statistics because what we're doing is we're doing what's called normalizing our values or standardizing the values. And we'll typically use them in other stuff. We're just not really going to talk about anything that really needs them. But if you were to go on in statistics and take a more in-depth statistics only class, you would probably use z-scores quite a bit. Even if you took like an in-depth probability class, you would maybe use them a bit. 2.5, there's also not a lot to say about it. It's just an important concept to bring up, which is the idea of correlation versus causation. Okay. It's important to bring up because we very often confuse these two. Okay. First of all, what does correlation mean? Well, it's really the strength of their relationship. So the strength of a relationship between two variables is called their correlation. Okay. So if and this would be like a numerical value. We're not going to go into how to calculate the numerical value, but again, if you went on with statistics, you would do this a lot. There's a whole area of statistics called regression, which looks at this correlation a lot. Okay. So if we say two things have a positive correlation, that means that as one increases, the other one increases. And if two things have a negative correlation, that means as one increases, another one decreases. Okay. So if we looked at the graphs of them, a positive correlation would look something like this. Okay. Where as one is increasing going to the right, the other is increasing too, going up. Okay, so this would be a positive correlation. And a negative correlation would be something like this. A negative correlation. So I'm just looking at the line here. These lines would be like our axes where our variables are. So I'm just looking at this line and this line. So on this one, as you go right, one of them goes down. Okay. So in both cases, though, they are correlated, meaning that there is a relationship between them. What this doesn't imply is that there's a causation. Okay, we often confuse there being a correlation for there being a causation. Just because as one goes up, the other goes up, it doesn't mean that one is causing the other one. Okay, they could both be being caused by something else. This is often incorrectly used when looking at articles about statistics. Okay. For example, you'll often see things saying like diet soda causes obesity. Okay. Which there's no data to show. What the data shows is that as more people drink diet soda, they tend to be more obese. But these are just two things that are correlated that are usually caused by something else. Like, for example, maybe the person has like diabetes, which causes them to need to drink diet soda, which is also a factor in their obesity. So that's driving up both of these things. It's not that the diet soda itself is causing obesity. That doesn't make any sense because diet soda doesn't have any calories in it, which is the only thing that could be contributing to obesity, right? So there's no actual research showing that there's a causation there. It's only correlated. But it's often in articles called a causation, even though that's not true. So like a lot of the time, we can really only show that there's a correlation. We can't show that there's a causation because there's so many things that could be causing both of them, right? Like in the real world, there's like with obesity, for example, there's like a million things that could be causing that. So it's almost impossible to rule out all of them and pinpoint it on one thing or even multiple things. Um, so at best, we can say that there's a correlation. Um, so this is really just something we need to be aware of when reading statistical articles, right? Um, Another good example of this is we'll often see like articles claiming that a lack of exercise causes depression. Okay. And you'll often see people saying, okay, if you want to cure depression, like to exercise more. But there's no real research that shows that there's a causation there. It's just a correlation, which makes sense. If you're depressed, you're less likely to exercise, right? And if you're not depressed, you're more likely to exercise. And that's only because depression is affecting your energy level. It's not actually because exercise or lack of exercise is causing depression or because exercise is curing depression, right? It's because of the energy level that depression leaves you with. So there is a correlation there. As you are more depressed, you are less likely to exercise. But that's because of this outside factor, which is the depression causing the affecting energy levels. It's not because exercise is curing depression or lacks of exercise is causing depression. Right? There's no causation there. It's just a correlation, but it's often misreported. And if you look at the actual researchers doing the statistics, they're never the ones claiming there's a causation. They're usually saying there's a correlation. But then somebody comes along, reads the statistical study, and writes an article about it for the general public, and they are typically misusing the words and using a causation. Or even if they use it properly, us, the general public reading the article will look at the word correlation and our brain will go, oh, there's a causation. And we don't really distinguish between them. Okay. So just know that there's a big difference between a correlation and a causation. And we need to be careful about which one we're using and about which one the articles we're reading are using. Okay. They're almost never establishing a causation, just a correlation. Okay. Um, all right. So that is it for chapter 2. Um, so thank you guys for watching these lectures. And I will see you for the next chapter. Like I said, make sure to be on the lookout for announcements about exam 2. And yeah, that's it for today. So thank you guys.